So our discussion in this lecture focuses around the concept of balanced trees and what they are and how we deal with them. So let's develop a notion of balanced trees. What do we mean by balanced tree? So we can give a very strong balance invariant that says a binary tree is balanced if all nodes have equal number of nodes in its left subtree and equal number of nodes in its right subtree. And so essentially we are talking about a tree like this. So that would be a balanced tree of one node. If you cannot have a balanced tree of two nodes, since this would be the structure of that, or a different structure. But then you can have a balanced tree of three nodes. Or you can have a balanced tree based on this definition of 7 nodes. So it seems to me that this notion of balance is really strong. And if you assume that the height of the tree, in this case, is 3, height is the number of nodes from root node to the lowest leaf, and we have the number of nodes in the tree in this notion of balance is 2 to the 3 minus 1, or 7 in this case, when you have a height 3. So that seems very difficult to enforce, as well as that it needs to have exactly this equation satisfied in order for the tree to be balanced. In other words, n equals 2 to the h minus 1. This is really hard to maintain. So let's try to make it a little more relaxing. So we're going to say now a binary tree is balanced if all nodes have almost equal number of nodes in its left subtree and almost equal number of nodes in the right subtree. So for instance, if I take this, that would be a balanced tree under this definition. And if I even take this, that would be a balanced tree. Or if I take this, a balanced tree of 3 nodes can be developed. Or you can do a balanced tree of 4 nodes, because you have almost equal number of nodes in its right subtree and the left subtree for each node. For instance, this one has 1 on the left subtree and 0 on the right subtree. So here's a balanced tree of 5 nodes. And so we can develop a balance concept like this. Here's a balanced tree of 6 nodes. So which we also know that these trees are called complete trees. So they are called complete trees. So this is okay, but only a special type of a tree can satisfy this invariant, which we call the complete tree. So that's the one notion of a balanced tree, which is more relaxing than the previous one, but it's still not good enough in practice, because we do not want the restriction that this tree imposes on us. A better balance invariant would be somewhere along these lines. We look at the height and we talk about the balance in terms of the height invariant. We say that at any node in the tree, the heights of the left and the right subtrees differ by at most 1. So for instance, here's a balanced tree under this invariant with 1 node. If you draw a balanced tree of 2 nodes, so this would be a balanced tree of 2 nodes. So here's a balanced tree of 3 nodes. But you can also have balanced trees in this form. You can have a balanced tree like that. That would be a balanced tree, because this one has, for each node, you will see that the height differ by at most 1. So let me show you a tree that is not balanced. For instance, if you take this tree, this is not balanced, since if you take the height of the left subtree for this node, that would be 2, and the height of the right subtree is 0. So the balance factors differ by more than 1. Keep in mind that the height we define as height of a node is the number of nodes from node to the leaf node, lowest leaf node. Or height of a tree is the height of the root node. So that's just to recall the height definition. So if we work with that invariant, which we call the ABL invariant, where we talk about the height differences as opposed to the number of nodes, we need to develop a schema or method to balance trees. So let's start here with the notion of a right rotation in order to balance trees. So you can think of a situation where you have a tree like this. Let's draw a tree here. Let's just say that we have 5 here, and maybe 3 here, 4 here, and 2, and 1. And then on this side we may have the tree which has 6 and maybe 7. In fact, let's just say 6. So clearly, if you look at this situation, that the left child of 5 has the height, that tree has the height 3. And the right child is height 2. So if you think about this tree here, that subtree, and this subtree, the height for this tree is 3, and the height for this tree is 1. Therefore, it does violate our notion of ABL balanced trees. So what we need to do is to develop a way to balance this tree by making some rotations. So one of the rotations we're going to be suggesting is to go to a right rotation around the X. That's where the balance factor is violated. So if we do that, we got to be careful about one thing. Now when we think about balanced trees, we always working with binary search trees. That means that this tree has order property, A less than Y, less than B, less than X, and less than C. That's the order that it needs to satisfy. All the elements of subtree A are less than Y. So after you rotate, you must have a tree which has a better height information, but also it must satisfy the order invariant. So how do we do that? Let's think about a balancing schema that we can think about something like this. We rotate it so that we will bring Y to the root, and then X becomes the right child of Y, and C is still attached to X, and then the left child of Y remains to be A. So we would bring up A a little bit higher, at least one level higher, but we have a problem with B. The problem with B is that the B happens to be greater than Y, so therefore it should be on the right hand side now, but less than X. Therefore it should be here. Now if you do that, our order invariant is still satisfied. So now we maintain a binary search tree still, but we hope that this new tree has better height information. So if you apply that same idea to the example I gave, it would look something like this. It would be that 3 would come to the top. You have 5 and 6, and then you have 4 becomes the left child here, and 2 and 1. Notice that now this is ABL balance, this tree, after you do the rotation around 5. So the next question we want to ask is that, how do we do this? How do we write the code to accomplish what we're trying to do? So let's think about a few things here. One is that the left child of Y, which is A, remains the same. It did not change. The right child of X, which is C, remains the same. But few other pointers have changed. Like for instance, the right child of Y is now something new. So this needs to be recoded. And also the left child of X is now something new. which is b. So that needs to be coded. So let's start by doing the following. We do know that after you write the code, after you do the rotation, the y would become the root node. So we will have to return that root node back to the calling program. So let's maintain a pointers to these things. Like say, for example, let's call this t, and let's call this the new root. Okay, so we know that the root is equal to t arrow left. We have to do all the null checks in here, keep in mind. And also we have to maintain that the root of, let's call this temp, because this, since that's going to change. So let's say temp is going to be root arrow right. Okay, now the question is, how do we write the code for accomplishing number 3? So the number 3 says that the right child of y. So the right child of y is called the root. So the right child of y must be equal to the old root, which is t. That's number 3. And then number 4 says that the left child of old root, so the left child of x is called t. The left child of x must be equal to the temp, which happened to be the right child of y. And now we must return the root. So this is essentially the code for right rotation. So let's do a quick example here. So we insert 5, insert 4, we are still okay. We insert 3. Now it requires a balancing act. So the balance would give me 4, 5, and 3. So after that, we're going to insert 2. 2 would go here. That's still fine. Then we would insert 1. At this point, a balancing is needed. So I'm going to be doing the balancing around the node 3 to get the following tree. So here I did insert AVL by doing a number of right rotations. Let's take a look at the left rotation case. The left rotation case is where you will go do the same thing, but you're going the other way. So let's try to create the same sort of idea here. The y would become the new root, and let's call this the old root t. And then we know that in order to maintain the balance invariant, in this case, I mean the order invariant, in this case c is less than x, less than b, less than y, less than a, we must get a tree that looks like this. It would be y at the top, and then you will have a attached to y, and then you will have x here and c attached to x, and the left child of y would become the right child of x. So let's make sure that's the case. So in this case, that the order invariant would look like this, which is what we expect. So this sort of a rotation would give us what we're looking for. So again, if you write the code, let's start by saying this is temp, root, and the t. So the code would look like this. Once again, the things that you need to change are the following. This link between y and a remains fine, remains the same. The left child of y becomes the old root. So this, let's call this the operation number 1. That needs to be changed. And then also the right child of x becomes the old left child of y. Let's call that operation b. So before we start 1 and 2, let's try to save the root. In this case, the root would be t arrow right, and temp would be root arrow left. Now keep in mind that you must do all the null checks before you do any of these things. Now let's write the code for 1. The 1 says the left child of y. Y is called the root. Left child of y must be equal to x. X is called t, so let's say equal to t. Number 2 says that the right child of x, the right child of x is called t here, x is called t, the right child of x must be equal to the left child of b, which is called temp now, so we're going to be calling it temp. And then finally you want to return root here. Okay, so this is the code that does the left rotation. So left rotation and right rotation are the fundamental rotations that you need to know in order to handle all the cases. So for example, I'll show you a simple one here. You go from insert 1, you don't need to rotate. Insert 2, you don't need to rotate. Insert 3, now you need a rotation. So you would rotate to the left and obtain this tree here. Now if you insert 4, no need for a rotation. And if you go and insert 5, you would get this tree. Now you need a rotation around 3 to get the tree, the following tree. So that demonstrates a series of left rotations that led to an AVL balanced tree. Let's take a look at the double rotation case. Now this is kind of tricky. So in some ways you can think about this as this is the way the balance was broken. Keep in mind that the balance breaks only when you insert something to the tree. So in the previous cases, we knew that the balance was broken when you inserted something all the way to the left. The balance was broken when you insert something all the way to the right. So we did a right rotation here and a left rotation here. Now we are looking at the other cases where the balance is broken when something like this happens. You inserted to the right child of the root node and the balance was broken. So in this case we need what we call a double rotation. The double rotation works like this. First you do a rotation around the child of x, left child of x. So here's what you get. You do a left rotation there. So you're going to get z here. This would be a. So you're going to get y and d. And this would become c. And then it gets b. Okay, then we're going to do a right rotation around x to get the following tree. Z, x, a, and then we will have y, d, and c. And the only thing we have to worry about is this left child, right child of z, which becomes the left child of x now. So once again, if you think about the invariants here, or the odd invariant, what you have here is d less than y, less than c, less than z, less than b, less than x, less than a. Now is that true if you come to this tree? Well, let's take a look at it. Let's do the in-order traversal on the tree. D less than y, less than z, less than z, less than b, less than x, less than a. So the odd invariant is satisfied. This is the same odd invariant as the previous one, although they are two different trees. And if you do the in-order traversal on this one, we know that d less than y, less than c, less than z, less than b, less than x, less than a. Hence the same order was obtained from that tree. Notice that we have three different trees, but gives us the same in-order traversal. Okay, so this is a possible double rotation case. So let's take a look at one example here. Let's say we insert 3, that's fine. We insert 1, that's fine. Then we insert 2. So this is where double rotation is necessary. So what we're going to do is we're going to rotate around the child first. So you would get 3, 2, 1. It seems like we're making things worse, but in fact, we're not making things worse, but we are preparing for the next rotation to the right around the root node. So a series of left and right rotations actually made it the tree we wanted. So that's the balancing part there. Now keep in mind that this was a series of left and right rotations, hence we don't have to code this again since we have the left and right rotation code. So here's the other case, double rotation, case number 2. So in this case, what we're going to do is we're going to be looking at, keep in mind, let me recall. The first case was that we looked at a case like this where we did the right rotation. We looked at a case like this and we did the left rotation. Then we looked at a case like this. We did 2 rotations, double rotations. Now we are looking at a case like this where you will have a situation like this. In this case, what we're going to do is we're going to do a right rotation around the child and a left rotation around the parent. So let's do that. So we'll have X. Let's do a right rotation so this doesn't change. So we will do Z here, Y and A and C, and this would become B. Let's make sure we did it correctly. So we can know that by traversing this by in-order traversal. So that's the order invariant that needs to be satisfied even when we traverse this tree here. So we do have the order invariant satisfied. So now we're going to do a left rotation around the root to get the following final tree. So the final tree would look like Z here and X and D, and then you will have Y and B and A, and the right child of X would become C. So let's do the in-order traversal again to make sure that we got the correct tree correctly. B and Y and A. So if you in-order traversal will yield this result here, which is what we expect. We expect the order invariant to be true no matter what the shape of the tree is. And we know that the final tree is better than the tree that we started with. So here's an example. Insert 1, insert 3, insert 2. So now we start balancing this tree. So the first is the right rotation around the child. That would give you 1, 2, 3. And then we do a left rotation around the parent. That would give you 2, 1, 3. So that is a balanced tree. So finally, we can try to summarize this by doing a number of AVL insertions. 12, fine. 8 is okay. 7, balance mess up, needs a balancing act now. So we're going to be doing 8 and 7 and 12. Let's insert 14. That's good. 18. Need a balancing act. We have to balance it here. This way we will do 8, 7, 14, 12, 18. Insert 10. 10 would be inserted into here. Now we need to do a balancing act because I think we have 1 and 3. So you need to balance it. So in order to balance it, what we're going to do is we're going to do double rotations. We're going to do it this way. So we'll get 8, 7, 12, 14, 18, and 10. And then we're going to do a left rotation here to get the 12, 8, 7, 10, 14, and 18. So, and I will leave the rest as an exercise for you to insert. So this is what we get after we insert the 10. So try to insert 22 and 15 and see how you can balance the tree. And this is the end of the lecture.